All right, so we're going to do two videos with related rate problems, and we're going to just start off with these and work our way up. So these problems are very wordy like this. Herpetologists have proposed using the formula S equals 1.1 W to the power of 0.2 to estimate the maximum sprinting speed S in meters per second of a lizard of mass W in grams. At what rate is the maximum sprinting speed of an 11-gram lizard increasing if the lizard is growing at a rate of 0.02 grams per day? Very wordy, very complicated. So what you want to always do is list everything. And following these steps here will work really well at breaking these problems down and make them very simple. Well, they're not going to ever be simple, but they will become a lot more manageable. All right, so what we always want to do is write down what everything represents in our formula. So S is our sprinting speed. And we do this so that we have a reference to know what letters we're dealing with here. And then this is in meters per second. And then our W is our mass, and that is in grams. So every time we see mass or grams, we know we're talking about W. And if we see meters per second and sprinting speed, we're looking for sprinting speed. Okay, I've already taken the formula and written it here. And so with each of these, you're going to need to use related rates on them. And we know the related rates because we're looking for the rate at which the sprinting speed is changing. Okay, so if S is equal to 1.1 W 0.02, that means we're going to need an S and we're going to need an S prime. You have a W, you're going to need a W and a W prime because we're going to take the derivative with respect to time on these problems. You can even see it here as per day. And so if you see per day, you know that's our denominator because it's over and it's day, which means we're going to need a dt. You can even see that the top was grams. And so that means we have a dw. So what they're giving you here is the dw dt, 0.02 grams per day. They gave you the rate of change. And it's asking for at what rate is the maximum sprinting speed of a lizard increasing. So that's our ds dt. That's what we're looking for. And then it says an 11-gram lizard. Well, we know grams is W, so we know that goes here for 11 grams. So by listing all the letters and their derivatives with respect to time, it gives us a place to fill things in. It also tells us what denominator we need. And so we know it was per day, so that's time. And so if we take the derivative with respect to time, we can find everything we need. So derivative of S is 1, so we end up with ds dt. Multiplying 1.1 by 0.2 gives us 0.22 W, and then we subtract 1, so 0.8, and then we end up with dw dt. And you can convert this to S prime and this to W prime. Just remember what they represent. So we really should write the units for S, which is meters per second, and time was in days. So it's meters per second per day. That's how fast its sprinting speed is changing. All right, and so if you've already listed everything up here, we can then just plug them in. So S prime equals 0.22, plugging in 11 to the negative 0.8. and then multiplying that by W prime. Okay, so plugging this in our calculator, we end up with this. So that's 4 decimal places to the left. So 0.1234. That's a 6, not a 4. 646. And then now we can go back up and grab the units. So it's meters per second per day. So we know its rate of change. And this is at that given moment. So this lizard weighs 11 grams. So at 11 grams, if its weight increases by 0.02 grams per day, we would expect a sprinting speed of this meters per second per day. So they work very similar, where you just take the formula, take the derivative, plug in all the numbers, but you do have to stay organized on what everything means. Take your time through each of these problems. So let's try another one. Okay, so let's try another one. Okay, so the dimensions of the juice box are given. The height of the juice box is being decreased by 0.5 inches per second. Find the change in volume when the height is 3 inches. And so we already know now that our dt will be our denominator, and that's when we're going to do our derivative, because it says the height of our juice box is being decreased by this, so it's giving us our rate of change. What we need now is a formula. So it says find the change in volume. Well, if we want to find the change in volume, we need a formula for volume. So that's where we want to start, is finding that basic equation. It's all been labeled with us here. And so we have our length, our width, and our height. And I know you want to use 6 for the height, but 6 is not fixed. See, 4 is a fixed value, 2 is a fixed value, the height is not. And let me show you why. Here's our juice box. Now watch what happens when someone starts drinking it. It starts going down. So the only thing that's changing here is the height. The width is not changing, the length is not changing, just the height. The liquid is being removed from it. And so that's what we're talking about here. These are our dimensions for it. We have our 4 inches, our 2 inches, and our x. And so these two are fixed, they don't change. This one's fixed, it doesn't change, but the height goes up and down. So if I fill it a little bit, this is now our x right there. If I decrease it, this is now our x. So you can see that it's changing, but this is still 2, this is still 4. They don't change. So when we create the formula, we have to use the fixed quantities and the variable. So 6 is not part of the problem. It's just telling us that the box is a height of 6. What we're dealing with is the liquid that's in the box. So our formula here would be V equals length times width times height, not 6. And so it would become 8x. And then now when we take the derivative with respect to time, we would end up with dv dt equals 8 dx dt, which means we need our dv dt. In order to find our dv dt, we need to have dx dt. So let's go back, and we've got our x written, our x prime, our v, and our v prime, so we have locations for them. So it says the height of the juice box is being decreased by. That's our rate of change, right? So that is our x prime. And it says decrease, so decreased is negative, and it's 0.5 inches per second. And I like to just put it on the side, inches per second. I was about to write it as a denominator, but no, let's write it as negative 0.5. And so now we can plug it in. And I like v prime, it's my preference. And I like x prime, and so that way I have a variable that I can just plug into. And this gives us v prime equals negative 4. Now you need units. And so if x is in inches, v, which we're looking for, is going to be in cubic inches. T is our denominator. So if this is dt is in seconds, this dt is also in seconds, which gives us inches per second. So when the height is 3 inches, right here, we expect it to be decreasing. The height will decrease at 0.5 inches per second, and the volume will decrease at 4 cubic inches per second. So 4 cubic inches per second to get to the bottom. So it kind of looks like this. It's just going to flow down. And you can see it's a constant rate going down. That's why we didn't need x to be plugged in here. So when we did this problem, find the change in volume when the height is 3 inches, our rate of change is already constant. So the rate of change in the volume is also going to be constant. And there you have it. We'll do some more complicated ones in the next video.